All right, I'm Otakar Nieder. I'm the CTO of Grip Studios, and I welcome you to my talk that I named Lag Compensation Techniques in a Physics-Driven Game. Just to manage expectations, this is not a generic talk about lag compensation techniques in any kind of a game. This is actually talk about one specific situation we got into during our development in Grip Digital. I will tell you more details about it later, but please, this is really like something that happened to us in a real life, so this is something that I can really talk about. It's not something generic. If we would talk generically about lag compensation techniques, we would be here probably 2 days. All right, so I will start with giving you some context so you understand why and how we got into the situation that we had a problem that we had to solve. I will start from a very wide angle, as you can see, but bear with me. I will get very quickly to the juicy technical things. So, as I said, I'm Otakar Nieder. I'm CTO of Grip Studios. Grip Studios is a company that has something like 120 people. We have offices in Prague and in Brno. And most of our developers are actually developers, programmers, sorry. So most of our people are programmers, and they work on external and internal projects. And before they work on our external or internal projects, they can go through our academy where we teach them how to work with Unreal Engine and about our processes and about what should they expect on the project they would be assigned to. So after that, they are assigned to one of our projects, either the external ones or the internal ones. And this talk is about one of the internal ones. For the sake of this talk, I name it Project K. It's not its real name. It's just the code name for this talk. And first, before still we go to the details, I will tell you something generic about the project. It's a Unreal 4 based project. It's not yet announced project, so I can't tell you much about it, unfortunately. Can't tell you everything about the game. I would love to, but I can't. And but I can tell you at least those details that will be needed for you to understand the problem. While the project is not announced yet and not finished yet, its physics part, which is actually the most important for this talk, is kind of done. We're happy with it, so that allows me to talk about it here at this talk, even if the game is not finished yet. So the physics is done. It's a physics-driven game. It uses a dedicated server, actually authoritative dedicated server, and it is not a game which would be focusing on one game mode. It's not an FPS, it's not a racing game. It's a game that has a different types of game modes, which is very important for what I will be saying later. But I will stop at that on the next slides. But first, I have a confession to make. I'm definitely not as smart as I look. I have thought about the idea for this talk, that's mine. I have actually prepared a skeleton for this talk, but when I started to put some meat on it, so it is interesting and challenging to think about, I find it out that I have to ask other people in our company to help me. And fortunately, my team is full of very smart people, smarter than I am. So they helped me, and the two people in particular who helped me with this talk are my two software architects, namely Michal Blažek and Ondřej Mocný. So in any time during this talk you think, oh, this is quite smart, or this is an interesting idea, that's very probably because I'm saying what they told me to say. If you at some point think, this is weird, maybe this is not interesting, well, that's probably me saying something they told me not to say. All right, so that's this disclaimer, and let's put together the pieces of the puzzle. So Kit Bash is a physics-driven game. We are using a heavily customized engine Bullet. We have interchanged it for the default engine, physics engine in Unreal, so we are not using the default one. We are using the heavy customized Bullet engine. And everything in our game, everything that's dynamic, is driven by this physics engine. So everything, characters, including the player character, all the dynamic objects that can just move around in the scene are simulated by this physics engine. So that gives us some kind of, that gives us nice interactions between players, so they can pull each other and push each other and in a very nice way. And that also gives us nice interactions between the dynamic objects. Just for you to have a slightly more idea about how the game works, we don't have only like some slowly moving objects. We have objects that can move something like 20 meters per second, maybe more. So it's something like a slower car. So that's something that is about the physics. Next one, we have a dedicated server which is strictly authoritative. That means that all the simulation, everything runs on the server. Nothing runs on the client. The client basically only just collects the input from the controllers. It sends it to the server somehow processes it and returns back some information about what should change visually on the client. So everything is simulated on the server. We do it for 3 reasons. One is security, because if nothing is happening on the client, nobody can tamper with that, right? So if everything is simulated on server, we have full control over that, and nobody can actually cheat in our game. So that's one of the reasons. Second reason is performance, because we really want to go pretty far with the physics simulation, and that takes quite a lot of resources. So, and we don't want to put this performance hit on the client station. We want it to run on almost everything. We don't want to aim for some fast PCs. So we push all the physics simulation to the server. So that is the performance side. And the last point is consistency. The server is the only source of truth in our game. Nobody just does any kind of simulation on the client, so we don't have to collect information from the clients about what they simulated and somehow translate it to the other clients. The server is the only source of truth for us, and that's very important for us because we want all the players to basically see the same thing at the same time. So that's about the authoritative server. Come on, yeah. And the last one is about the emergent gameplay. So as I said, our game is not a FPS. It's not a racing game. It's not an RPG. It's not a strategy game. Our game is a game where you can play in different modes, and different players that are playing together can actually do something a bit different, and all of these modes are of the same importance for us. So we do not want to somehow prioritize shooting. We don't want to prioritize driving. We want all the things to be of the same importance for us. And that has a big plus, because it gives our game pretty, sometimes unpredictable, but most of the times very enjoyable and funny situations, which is great. That's what we are aiming for. But there is a technical problem, because all the lag compensation techniques that you might actually know are usually tailored to some type of a game. So if you have an FPS, there are lag compensation techniques that you can use for FPS, and it will always work for that, and it will give you a good experience on the client. If you have a racing game, it's the same. There are different lag compensation techniques, but again, there are some that can be tailored to that, and that way you can have, again, a very nice multiplayer experience on the client. But for us, we have different gameplay modes, so that is pretty challenging on choosing the right lag compensation techniques. Finally, we get to defining the problem. And we start with looking into what happens when you push a button on a controller, on a mouse, or something like that, and what happens all before you see the result on your screen, on your client. We start from the left on the client simulation line, and we go to the right. So you press your button, that is collected, and during the same frame on client, it is sent to the server. So you're crossing the network layer line, so that it means that it is sent somewhere over the network. And then on the server, there are three things that have to happen. First, the input needs to be processed. The result of this processing needs to be fed into the physics. Physics somehow crunches on it, creates some output, puts it into the logic box, which is the one that calculates game logic, all those things that should happen in reaction to what happened in the scene. And from that, the information that was calculated through these simulation steps goes back to the client into something called jitter buffer. I will just talk about it in a second. Then on the client, it is sent to the renderer. The renderer does some kind of a smart interpolation and renders it. Right. So, whoops. That red line, everything that is in those bounds of the red line is basically the time that you are waiting, or kind of contributes to the time you're waiting for the reaction to your input. All of that has to happen, and then you see the result. So when we saw this kind of chart we have drawn, we started to think about, okay, we want the input delay as short as possible, because if it would be very long, let's say, and I'm exaggerating now very much, 10 seconds, you would be waiting from pushing a button to seeing the reaction on your action for 10 seconds, and that's definitely not engaging and not a good gameplay, right? So we are trying to make this as short as possible, and that's our problem. How to make this as short as possible, the red line. When we looked into it, there are a few things that we can actually shorten or work on so it is short as possible, and there are a few things we can't do anything about. And those are the arrows that cross the network layer line. We can't do anything about it. That's dependent on your connection. We are sending something over your network connection, and basically we can't do anything about it. So we only can somehow mask the effects of this, and I will talk about it later in this talk. But we can do something about the input processing, physics, logic, and jitter buffer. We can make them as short as possible. For the sake of this talk, I will assume that the input processing and logic processing is optimized as much as possible. So I will basically neglect those. They have their own problems, but it is not actually important for this talk. So what I will be focusing on is this. Don't know what I pressed, sorry. Děkuju. Okay, once more. Come on. So we will be focusing on these purple squares. One is physics, one is jitter buffer. What is jitter buffer? Maybe a lot of you are aware what jitter buffer is. It's kind of a technique which is used in many multiplayer games. On the client side, you have a buffer where you're storing information that comes from the server, and you save it there for some time, and then you use that information to interpolate between those pieces that you got to get exactly what you need at the time you need it in the client. It's kind of complicated to think about it, but actually it's nothing too hard. You basically have some kind of a buffer where you are first waiting for all the information to stack up in, and then when it is filled, I don't know, after 50 milliseconds, you use it to interpolate, and you get exactly the information that you need at the time when you need it on the client. Usually, the jitter buffer is of a fixed length, so let's say, it has 50 milliseconds, as I said. So you're waiting for 50 milliseconds until you have all the information you need, and then you use it for the interpolation, and then you put it to the renderer. But that is not good enough for us, because that means that there is 50 milliseconds we are waiting. We don't want to be waiting. We want the jitter buffer to be as short as possible. And we can do that. We can have the jitter buffer of a variable length, and the length is dependent on how is your connection, what is your quality of your connection, basically on a ping. We know what your quality of connection is, and we can just shorten it or make it longer to have only the data we need to do the correct interpolation, nothing more. So for a not quality connection, it can be long, but we can't do anything about it. So we already have a big latency, so we are adding something to it. But for a good conditions, we want it to be short. We basically want to have only two pieces of information there to interpolate through, or maybe even not that and use extrapolation. But basically, we want this to be as short as possible. I will talk about extrapolation later. It's just here. If we don't have anything in the jitter buffer, we have to have some way of extrapolating from what we already have to get some data that we can feed to the renderer. All right. So this is jitter buffer. Unfortunately, I have clicked once more, and I have already revealed the physics field. Shouldn't have been there, but it is. So now let's focus on the physics. That's the most important and interesting thing in this talk, actually. So how does it work? The physics simulation receives something we call commands. Commands are some data structures that contain information about what forces and impulses and torques should be applied to what objects. That goes into the simulation, and that tells the physics what it should add to what it already has in the physics scene. The second piece of information that is in the command is a time for which the time the physics should be calculating. And this is a bit complicated, so please make a bit of attention, because we tell the physics to simulate, let's say, 10 milliseconds, okay? But that means that the physics will go 10 milliseconds into the future. It will try to simulate these 10 milliseconds and then return the result. It doesn't mean that it calculates for 10 milliseconds. Because calculating these 10 milliseconds of time can take, I don't know, 2 milliseconds because there is nothing in the scene. But it can take 15, 20, maybe 30 milliseconds if there is something very heavy happening in the scene, like things flying around, interacting, bouncing on each other, okay? So we say that the physics has a step of 10 milliseconds, and that means that it tries to simulate 10 milliseconds, but not that it takes 10 milliseconds. So please keep it in your head, because that's important for the next slides. Some things we have found about our physics implementation, the customized bullet engine, is that the longest step that the physics should simulate is 11 milliseconds. After that, we are not getting consistent results. So 11 milliseconds is the longest that the physics should try to simulate. And the other thing we found out is that it's better on the same input to do 2 of these steps and then receive the snapshot, which is the result of the physics, and not take the snapshot after every frame of the physics. There are reasons for that, but I'm not going to get into the rabbit hole because it's very, very, very deep. So just keep in your mind, we always have to do 2 steps of, let's say, 11 milliseconds to get the right results, so we get a deterministic and precise physics. Okay, so we know that. So once we knew everything, all of this, we started to think about what we can do to make the physics not tamper with our frame rate on the server. We want to have a server that has very frequent ticks, and they basically, it's always 120 hertz or 60 hertz or something like that. We don't want the physics to be longer and shorter and longer and shorter and basically make our server tick longer and shorter. So first thing that you probably also think about, let's make it parallel. Let's put it on a different thread. Let's make it parallel, and it will be solved. And we were like, oh yeah, that's cool. So before we started to do that, we were like, we are assuming that our physics will most of the time actually take more of those more than the 11 milliseconds. So it will be calculating the 11 milliseconds for longer time than 11 milliseconds. And we made the assumption that it will be quite a lot longer. So that got us to the situation where we really put the physics on the parallel thread and made it totally independent. So the physics is just basically calculated on a different thread, on a basically totally parallel thread. We feed it with the commands. Those commands go to some queue. Physics takes them when it wants, and then it returns us the results after it has made its 2 steps. We don't know how long the steps are. We're just happy that we have the results. This was a good thing until we found out that our physics actually doesn't take that long, that our physics is most of the time doing well. And we were like, hey, that's cool. Our physics is doing well, so we should not have any latency. We should not have any delays in getting the physics snapshots and then getting them back to client, right? But there was some problem. We were still getting variable latency. We sometimes got more than 10 milliseconds of latency. Sometimes we got like more than 2 milliseconds. Sometimes it was okay. Why? Finally, another picture. So this is what we have implemented. The physics is trying to simulate 11 milliseconds of 11 millisecond steps, and it's actually getting pretty well. This is a bit simplified picture because the steps are not all the same length, but just for making my case, this is totally okay. The server, we said it should be really fast, 120 hertz. That means that each of the frames is 8 milliseconds. So frame 1, frame 2, frame 3 is 8 milliseconds. The physics is running on, let's say, each of the step takes those 11 milliseconds which we wanted to simulate. So what happens? In frame 1, we feed the physics with the command. But it is already doing something, so it's just not picking it up. And once it is done with the step 1, it will pick up the command. But we are already in frame 2, so in first frame we didn't get any result. In frame 2 we didn't get any result. In frame 3 we didn't get any result. In frame 4 we didn't get any result. In frame 5 we got the result, because we have to do the 2 steps. And then we just look into the physics and it says, yeah, I have the snapshot, take it. So the physics is doing well. We would like it to return the snapshot to us, maybe the second frame, or even in the same frame, not waiting for 1, 2, 3, 4 frames to have the result. Because each of the frames is 8 milliseconds, so that's 32 milliseconds we are waiting for the result. It could have been 8, it could have been 16, it's 32, all right? So next one is similar, but maybe better, because the synchronization, or not the synchronization, but the steps of the threads are actually pretty desynchronized, and we are getting the data in a kind of a random time, to be honest. So this is not great, because we do not have a control over the latency. It just is longer, shorter, and that's not what we want. We want it to have totally under control. All right, so back to the drawing board. What we have done is that we have left the physics on its own thread, but we have synchronized it with the game thread. So now what happens? First, what we have done is that now the one frame on the server, the game thread, the lower one, has 60 hertz, runs with 60 hertz. So one frame has something like 16 milliseconds on the game thread. And we said we want to wait for the physics up to 75% of this time of the game thread. And if it is done by then, we can still get the results. So what have we done? On the simulation, on the physics simulation thread, we said, okay, so 75% of the 16 milliseconds is something like 12 milliseconds. So each of the steps of the physics should be simulating 6 milliseconds, and we hope that it will actually end in 6 milliseconds. And to our surprise, it worked. Like most of the time, we are able to get the results of the physics simulation in the same frame. It's a longer frame. It's not 8 milliseconds now, it's 16 milliseconds now, but that's much better. We are getting it in 16 milliseconds, not 32 milliseconds. So it is very important to think about, if you're doing the parallelization, to think about what is the interference of the threads and how am I actually synchronizing them. So this is the ideal condition. Everything works well. We're getting the snapshots from physics as soon as possible. So our latency is under control. The physics is as short as possible. But of course, the world is not an ideal place. So what happens if the physics gets behind? So first, it could be this situation where the physics in the first frame took longer than the first frame. So the game thread didn't wait for it. We're not waiting until the physics is done. We are only waiting if the physics is done in 12 milliseconds or less. If it is not done in 12 milliseconds or less, we just go, and we just unblock the game thread. So if the physics is not done, it just goes and simulates. The game thread just doesn't send anything to client, right? That's not a problem for few frames because we have the interpolation and extrapolation algorithms on the client, so that's not a problem for us. Because next frame, the physics can just get back to its normal, very quick calculation, and we could be good. So on the next frame, we store the snapshot from the previous simulation, but here we find out that we have a new snapshot, so we throw away the previous one and send a new one. And again, we're back. We're back to the speed we need, and we have the latency kind of under control, right? We have one frame, just basically one snapshot got away, but we don't mind. That's all right. Everything is going still pretty fast. Well, now, if 2 frames are too late, we are starting to get into a problem. Because the latency is getting longer and longer. And again, we need to have as short latency as possible. We don't want it to just go out of control and be out of nowhere 3-4 times bigger than what we expected. We want to have control over it. So here we are losing control over the latency because physics is getting longer and longer. We are not getting the snapshots in the 16 milliseconds, but we are getting them in those 32 milliseconds where we were at the start. All right. So what can we do with that? How can we get the latency back to control? Well, because we are programmers and we can do everything, we slow down the time. So now we say, hey physics, you are overloaded, so we will help you. We will shorten your step to, let's say, 8 milliseconds, not those 6 and 6, but 8, and we will do only 1. We are not getting as precise results because, as I said, we need to always do two steps. But anyway, we don't mind. We are solving a bigger problem. We want to have a latency under control. So now we are actually waiting for 12 milliseconds to simulate 8 milliseconds of time. So we're actually like slowing down time. The simulation of the physics slows down, but that's okay because yes, you feel slightly like moving in honey, but you still have the responsiveness. And that's one of the most important things, responsiveness, right? So you have it, just your time is slightly slowed down. And the last thing that could happen is that the physics gets out of control totally. And what we do, we return back to where we were at the start. We just make it fully parallel, and we just from time to time check for the snapshots. We can also still more slow down the time, but we are basically now out of control. So what do we do? In this case, we hope. We hope that it will get under control soon, because we don't think that something physically simulated will just go forever in the scene. It will there will be things that will bounce into each other, and they will just level down, and everything will be calm again. And once we find out that the length of the simulation of the physics is getting down, we can go back to what we had. Basically, we can backtrack through those through those pictures back to the start. So that's basically our solution for the physics part. So what we are doing, again, like just a recapitulation on the physics side. Parallel physics, it's great. It's awesome. Parallelization is one of the things that makes things faster. On the other hand, it's not as great for when we don't have a big load of the physics. So it's great for when your physics is just really overloaded. It can just somehow do it on a separate thread. You don't have to care about it. From time to time you have a result. Great. You have a bigger latency, of course, but your physics is already anyway struggling. So it's probably not that big of a deal. Still a problem, but there is already happening, quite a lot of things is happening in the game. So you probably can say this is okay. But for the cases when the physics is doing well, as we saw, it's not as great. So you always have to think about, as I said, where are the synchronization points of your threads? Is there any kind of interference? Do I have a control over what is over what the other thread is doing? And so for us, in this particular case, for our game, we are using the hybrid solution. First, we start with the synchronized physics, and when we find out that it's starting to get slower and slower and slower, we are doing all those things that I showed. And at the end, if it is still very bad, we just go to the parallel physics. So that's what we do, and we also embrace the fact that the time can slow down. Okay, that's what I said. The time can slow down, and it's totally perfect for us. We made it part of our game. Okay, if there's a lot of stuff happening, we just slow down the time. All right, so that was everything about the physics. And about what we can do about the jitter buffer. As I said, we can really work with it to make it as short as possible. And about the physics, we can just do it parallel or synchronized and make sure that we have the highest control over the latency as possible. Now, we can do also something to fight the latency on the network layer. It's nothing much, but it's more of like a magic and smoke and mirrors. But it's not that technical as it was before, but we can still do something. So first thing we can do is, I already mentioned that, we can have the highest possible control over the jitter buffer length. And that is possible because we have a very highly synchronized time between the server and the client. The client always knows what exactly the time on the server is, so which information from the jitter buffer to use. And that means that we can really make the jitter buffer as short as possible. We don't have any kind of a 10 milliseconds here and 10 milliseconds there difference, and we really know down to millisecond what's happening there. You might be thinking, oh, that's normal, that's something I would do. Be aware that when we use the Unreal 4 implemented synchronization, that was not working well, and we were getting desync, so we have written our own time synchronization, and now we have a full control over that. Another thing which we can do, and I already mentioned that, is to fight with the times when we do not have enough data in the jitter buffer. When it can happen. It can happen if we are not getting enough information from the server. That might be because the physics is really totally overloaded, and with several frames we do not have any information. Or it can happen if there are any kind of network glitches. So the server wants to send something, but the network connection is so bad that you can't get it. Of course, extrapolation, if you have ever tried to do that, you are basically working on the past data to look into the future and try to simulate what would happen based on those data in the future. future telling is not reliable. Just sorry to say that, but it's not reliable. So the more you get into the future, the more problems you will encounter. And you will see all these visual glitches like teleporting and these kind of situations which everybody hates. Two players see something different. One player sees that they hit the other player and that other player should be dead, and the other player just sees that everything was okay. And one of them will die or maybe not die, and one of them will be definitely unhappy. So those things happen if you're using extrapolation for too long. We have found out that, again, for our game, our extrapolation algorithm can work to up till 100 milliseconds of not having data. If we don't have data for 100 milliseconds, it's okay, we can cover for that, but above that, we can't. You will start to see these visual glitches. So what else can we do? We can really start to fake things. If you basically, if you remember that diagram that was showing how long it takes or what everything has to happen between you press the button and you see the visual difference, you can actually start to do something on the client before you actually get the information back from the server what really happened. That's getting into the area of predictions, which I will be talking about just in a second, but we can make some assumptions. For example, our character has a capsule which, if it rotates or if it makes direction, it doesn't affect the physics in any way, right? It's just some kind of a cylinder or something like that, that it rotates and it has no effect on anything that is happening in the scene. So what we can do, if you press your stick to the right, we can start to change the direction of the character to the right with pretty good probability that we will be the same, that the results on the server will be the same as what we are doing on the client. So we can do that. We can also start to prepare animations. For example, if you press your button forwards, or your stick forwards, you expect that your character will start to run or go or walk or something like that. So we can start to just, I don't know, move the feet of the character slightly, not moving the character, but start the animation of walking, and until it seems really unnatural, you get the information from server confirmation, you can move forwards, and you start to move. And maybe your character will slightly step on the spot, but you at least have some visual reaction to what you are doing. So we are kind of messing with your brain, but it usually works for a short time. Of course, if it is for a long time, then you will see, then you will just say, oh crap. The last thing we do is something we need to do, but we're not happy about. Because you can shoot in our game, and we know that aiming is really, you want to be really precise if you're shooting. We are implementing a prediction of where we think that you will aim, and we are sending that information to the server. So there is something where the client says, well, you know, server, I know that you're the authority here, but please, can you consider this? And we send them the direction where we think that you should be aiming, and the server can calculate with that. That goes against our security point, because you can make aimbots using that. If you want to hack our game, you can make aimbots. So we're not happy about it, but we are ready to bite the bullet. Prediction. Maybe some of you who work in the multiplayer area for a longer time are screaming in your head saying, hey, why don't you do prediction? Why don't you do prediction? And it all goes down to the fact I was saying about the emergent gameplay. You can do prediction if you know what is the priority of your simulation. If it is FPS, yeah, my priority is shooting, so I will do some kind of predictions around the area of shooting and running maybe. If you have a racing game, you will do some predictions when it comes to the movement of the car and other things. We can't do that because our game modes are not exactly these. They can be those, but we don't know in which time they will be, one player will be using this and one player will be doing that. So we can't do that. We just can't predict. We cannot do anything on the client. Prediction, I should have said it at the start, is some basic forward simulation on the client. You would just do what the server does, but on the client, and predict what the server would probably come up with. Another reason why we can't do that is that physics simulation is very often not deterministic. I said that we have a fixed step of the physics, so that means that our physics should be deterministic, and maybe it is deterministic on one platform. But what if we want to have our client on a different platform than the server? Different platforms, their float calculations, which are very important for the physics, as you can imagine, could be slightly different. Right? We can get to different results on the client and on the server, and as again, you very probably know, these small differences have the tendency to accumulate, they like each other, and out of nowhere things are flying into the space. So again, our physics should be deterministic, but we don't trust that it is deterministic and it will always be deterministic. Again, that's why we don't want to do prediction on the client. But the biggest reason for not doing that is the performance of the physics. As we have seen before, the physics can take quite a long time to calculate, and we do not want to push it on the client. Especially, again, maybe some of you know, prediction comes with rollbacks and resimulation. What is it? If you start to predict something on a client and you say, hey, well, the character should be 1 meter in front of its current position, fine. But the server simulates the same, and actually the server knows that there is another player going from the right and pushing and hitting your player. So you will find out that you actually on your client moved 1 meter forwards, but during that somebody hit you, and at that point server sends you, no, your information is not correct, you have to resimulate. You have to roll back to the time when I actually found out what happens, and then resimulate to your time. And those resimulations can be several frames of physics. And again, as we saw, 1 frame is quite a long thing. So if you would do it on the client, you would have to maybe resimulate 5 frames. That's a long time. So you could actually have a problem with performance on your client. Again, we don't want that. So that is why we do not use any kind of prediction. Those are the reasons why we do not use any kind of prediction instead of extrapolation, which is kind of a prediction, and these kind of smoke and mirrors effects. Fine, I think we're getting to the end. So what I hope you will get out of my talk, I hope you heard me because I'm just moving my microphone, but hopefully you will get something from my talk, is that latency is our enemy and it should not be underestimated. Please, if you're doing a multiplayer game, please always think about the latency and fight it as much as you can. Sometimes you can't fight it as good as I said, some FPS games or whatever, because you have a different game mode, but you should always make all the effort for the latency to be as short as possible, so your player has the best emergent feeling from the game. So that's one thing that you should take out of this talk. Second thing is our sad experience with parallelization. Well, maybe not sad, but definitely not what we expected from it at the start. It's not always the cure. Make sure that you understand what your parallelization is doing, how your threads are actually interfering or maybe not interfering. Another thing, physics simulation prevents prediction. I spoke about it a few seconds ago, so I will not repeat that, but basically we do not do that because of the cost. That's the biggest reason. I mentioned other reasons, but the cost is the biggest reason. All right, I think I have said everything I wanted, so please visit our booth in the lobby. There still might be some beer, so you might want to go quickly before it's done. It's gone. And now it's the time for your questions and hopefully my answers. All right, nobody has any questions? There is one.
Hi, Thanks for the talk.
Thank you.
So you were saying that the first thing that you do if you see some problems with the simulation on the server is that you slow it down, right? So you do, instead of doing 2 steps, you do 1, so to say. So do you consider during the gameplay, like I imagine that if you slow down the simulation, it start to go well and working. Do you consider speeding it up again at some point, thinking, okay, we're fine, then can we speed it up and bring the best experience to the player again? Like, thinking if we're fine with the faster simulation at the point.
Yeah. I apologize if it was not clear from what I said, and it's very probable that it wasn't. We do that. Once we find out that the physics starts to get okay, we speed up the time again, and we go back to what I said, 6 milliseconds of simulation, and everything is okay. So yes, we do that. It would be very bad if the game just got slower and slower and slower and slower. So yeah, we definitely do that.
Hello, so really great talk.
Thank you.
I have got a question. So if there is a moment when physics takes too much time, would it be reasonable to turn off some of the non-essential physics simulations, like for the far objects or invisible things or whatever that is not important right now? Thank you.
Yes, that's a very good point. There is one issue, and that is that everything is important for us. So we almost always simulate all the stuff that is in our scene because we want the experience to be as good as possible. So almost everything is always simulated in our game. We sometimes sleep the physics on some objects slightly faster than it would be normally done. But usually we simulate everything, and it's because of us.
Hi, Otakar. Thank you for the talk.
Thank you.
I want to know sort of the design behind the slowing down time. Do you plan in your game to notify the player that the time has been slowed down, or do you want to play like a dead mouse that just, if he doesn't notice, then everything is fine and we won't tell him?
What to say about that? And not to reveal too much. I think currently we do not have any kind of indicator like that in the game. And I don't think we will do that unless it starts to be really a big problem. Because I'm saying that we slow down time, and you might be imagining that the game goes, I don't know, 2, 3, 4 times slower. It's not that bad, right? It slows down a bit, but most of the times you should maybe feel it, but very quickly it should recover. So currently we do not have any kind of a indicator there. And again, it kind of it kind of is okay with our emergent gameplay and about what we want to do. So we're pretty lazy about it at this point.
So, what about solution about faster servers?
That's a good point. That's a very good point. Yes. We have already quite fast servers. The thing is that the physics, again, I can't tell you. I would so love to tell you. But the stuff that we need to simulate there is a lot of it. So yes, faster server would solve it, but basically only push it a bit more. So we still need to solve that. So yes, we can go for faster servers, and we are now using quite fast servers, but there will always be this problem. Faster server is only pushing it to the future. And so yeah, that's that.
Okay, thanks.
Hi, Milan.
Hey, so when you are saying that if you have time and you are not slowing time, you simulate 2 frames on physics. What do you do with those frames when they are received on the game thread? Like, do you throw away one frame and just using the last one, or you simulate or interpolate between them?
We only send the second one. So we throw away basically we don't even like ask the physics for the results of the first frame. We just tell it simulate 2 frames, and then we ask for the results. So we don't use the first one.
Yeah, okay, thank you.
You seem to have good statistics about the frames and physics length. Is there a possibility to somehow not predict, but maybe estimate how long the calculation will take before the start?
Not to our knowledge, to be honest. You have to make the simulation to know how long it takes. So, no.
Great talk, Otakar. I will ask you about that rabbit hole later. But now I have a question. Of course, it's obvious that you want to have fixed frames. You mentioned 8 second, or sorry, 6 milliseconds and then 8 milliseconds. Do you have more variable durations or just these two?
I know about these two, but I think that the current simulation is that there are more of these values. We're just slowly getting to a shorter time frame. So it's not like steps, but it's like shorter going to. So there definitely are more of these.
Okay, thank you.
Mm-hmm. All right, I think. Oh, there's one more question there. That would be probably the last one because we're getting out of the time. So.
Hi.
Hi.
I was wondering, it might be asking like to reveal too much, but like the server architecture, are you using like bare metal or are you using some of the existing solutions? Like, I don't know, Kubernetes multiplayer or something like that?
We are using bare metal.
Okay. Thanks.
All right. Thank you very much for your attention, for your questions. It was great to talking to you, and I will see you maybe at our